Hi, my name is Mackenzie Poncel, and this is my Physics 2211 Lab 3. In this lab, we're going to create a computational model of a star traveling around a black hole. We use Python to code a model for the star's motion. We will iteratively calculate the net force acting on the star, thus determining the mass of the black hole. We're given the star's mass, position data of the star, time between data points, and the position of the black hole, which is the origin 0, 0. We're able to use the momentum principle to calculate Fnet. We find that the initial momentum and the final momentum is equal to our star's mass times the initial and the final velocity. We can then calculate the change in velocity and momentum, and we store these values in delta V and delta P. From here, we can calculate our dP over dt, and then we can use Newton's second law to calculate Fnet. Below that, you can see we decompose the dP over dt into its parallel and perpendicular components. We can mathematically equate these components to the Fnet parallel and perpendicular components. You can see in the code how we did that by determining the Fnet parallel and the Fnet perpendicular. For this problem, our interactions include the system, which is the star, and the surroundings, which is the black hole. The net force is only comprised of the gravitational force of the black hole on the star. You can see here we equate the magnitude of Fnet to the gravitational constant multiplied by the product of the black hole's mass and the star's mass. This is all divided by the distance between the black hole and the star, which is squared. Here is the glow script code that will determine the net force. We input our GT email, which then creates a unique set of position data points of our star. We have our system properties and initial conditions. G is the gravitational constant. The mass of our star is given to us as 2 times 10 to the 30th. Our delta T is also given to us as 1 day, and here you can see we calculate that time in seconds. We're able to calculate the x components of the velocity, and using this while loop we calculate the y component of the velocity. From this calculation, we're able to use another while loop to find the initial and the final velocity. We're able to compute the initial and the final momentum vectors. From here, we're able to use Newton's second law to calculate Fnet. We're also able to break Fnet up into its individual components of parallel and perpendicular motion. From here, we can calculate the mass of our black hole. Our code calculates an average distance between the star and the black hole to be 3.75 times 10 to the 12th meters. The ratio of the arrow length is 1/3 of the average distance. The net force is determined to be 9.627 times 10 to the 28th newtons. Therefore, our arrow scale is given to us as 1.3 times 10 to the negative 17th power. We will now run the code to see the model of the star's motion. As the code is run, the magenta arrow is the Fnet parallel, the cyan arrow is the Fnet perpendicular, and the orange arrow is the Fnet. Notice how the magnitude of the arrows change as the star gets closer or further away from the black hole. Our code prints the mass of the black hole after each iteration. It also prints the value for Fnet, Fnet parallel, and Fnet perpendicular. It gives us our average star position of 3.75 times 10 to the 12 meters, and it also gives us an average black hole mass of 1.34 times 10 to the 34 kilograms. Assuming that the net force was constant and there were no other interactions, by observing the motion of our star, we were able to determine that the gravitational force is the only force acting on our star. From here, we're able to determine the black hole's mass by equating the Fnet as the gravitational force. We did have variation in the black hole's mass from iteration to iteration. The mass varied from 1.27 times 10 to the 34th to 1.4 times 10 to the 34th. This shows that our model is not perfect and indicates that a net force must not be constant, or there must be other forces acting on the star. Mathematically, the rate of change of momentum with respect to time is equal to the net force. We can decompose the rate of change of momentum into its parallel and perpendicular components. This is also true for the net force. The individual components of the net force and the rate of change of momentum can be thought of as a cause and effect relationship. The components of the net force cause the changes in the momentum components, and this is how we perceive the motion. What if we were to replace the known black hole with a new one? Assuming that the motion of the star is unchanged and the only force is still the gravitational force, we would not find a different mass for the new black hole. This is because the net force is found by observing the motion of the star. Since the motion is the same, we will not find a different force. If the force is the same, the mass of the black hole will also be the same.